Hello everyone, welcome to this video tutorial on a finite element analysis, a practical approach using ANSYS. So myself, I am Shankar, Assistant Professor from Mechanical Engineering, Tyagarajar College of Engineering, Madurai. So before getting into the analysis, so I would always start with the steps that is involved in solving a problem in FEA using any FEA softwares. So there are basically three steps: pre-processing, processing, and post-processing. So we have a list of activities that you have to do in the pre-processing stage. Then you will go for the processing, and finally you will see the results in the post-processing stage. Right. So today we will be seeing the sixth video tutorial in our series. So far we have completed the 5, and the sixth one is determination of buckling or crippling load in a long slender column. Basically it is a buckling analysis what we are going to do today. Right. So let me directly get into the problem. Okay, so I have a long slender column of rectangular cross section of length 10 meters, right? So what I'm going to do is basically, I'm going to convert this three-dimensional column into a one-dimensional column using this concept of constant cross section, constant geometrical area. So I have a rectangular cross section of breadth 300 mm and width of or height of 500 mm, and the entire length of the column is 10 meters. It is made up of a material of Young's modulus 200 gigapascal and Poisson's ratio 0.3. So I need to find out the critical load in order required to buckle this column. So I need to find this PCR. So this is my ultimate aim of this exercise. Okay. So I have converted this three-dimensional problem into a one-dimensional problem similar to this, right? So let me start by solving the problem, right? So before going to that, let's see. So I'm going to choose the element. So here as I have converted the problem to 1D, I'll be using a one-dimensional element, which is beam 2 node 188 element, which we are very much familiar in ANSYS. So you can find here beam 188 is suitable for slender to moderately stubby or thick beam or bar structures. So it can be used to solve the buckling problem also. And next stage is material properties or section properties. So material properties have already been given, and section properties, we have a section of 300 mm and height 500 mm. So I'll input that in ANSYS. Next, modeling the problem, which it is a very much simple model. So we are going to keep two key points. One is 0, 0, 0, and as the height is 10 meters, I'm going to input it in mm. So 0, 10,000, 0. So I'll get your model. And next, you are going to mesh the problem. So you have there is no need to do this mesh attribute because you have a constant cross section and the material section is same. You only have to divide the segments and mesh. So this mesh attributes in this case is not necessary. And the next stage, boundary conditions. So here in column we have 4 boundary conditions, right? So one end is fixed and other is free, and one end is fixed and other end is hinged, and both the ends fixed and both the ends hinged. So these are the 4 boundary conditions which are available in buckling. So we are going to see all these one by one. So first boundary condition that we are going to see is one end is fixed and other end is free. So this is my problem. I have fixed in the bottom and the top. So this is a dummy load. I'm going to apply a load of 1 Newton in the downward direction, which is called as a dummy load. Actually, the aim of my problem is to find out the critical load PCR. In order to find this critical load while solving the problem, I'm going to apply a load of 1 Newton, which is a dummy load. It does not have any significance in the output. So I'm going to just apply the value of 1 Newton here. So this is just a dummy load. And after applying this, I'll finally find out my critical load. I'll tell you how it can be done, right? So before starting ANSYS and seeing how to solve this problem, let me give a short introduction on buckling. So you know that, so what is basically buckling? So consider 2 columns. So one is a short column where the length is very much shorter when compared to the cross section area of the column, and another one is a long column where the length is very much higher when compared to the cross section of the column. In both the cases, you are applying a particular load, and I would like to know when this short column will fail and when this long column will fail. Precisely, you definitely know that the short column will fail by crushing or compression strength. So the compression stress, compressive stresses is nothing but load by area in a simple bar. So there is nothing but a short bar or a short column, right? So when this compressive stresses exceeds the yield strength of this particular material, yield or ultimate strength of this particular material, then this column will fail. Whereas in long column, unlike in short column, you have a load which is called as a critical load. When this load occurs, the column will tend to buckle like this. So this is called as buckling. You would have experienced this buckling using a steel rule. If you have a long size steel rule, you could easily find this buckling happening. So you hold the steel rule one end on your hand, and if you apply a load on the other end, you can easily find that the steel rule will become a shape like this. It will tend to buckle, right? So the failure in a longer column occurs more due to buckling than compressive stresses, right? So this PCR, this critical load, can be calculated using the Euler's column theory, using the 4 conditions, and the formulas are given here, right? So I'm going to solve my problem, right, using all these 4 conditions, and I'm going to verify whether the analytical answers that I get here matches with the ANSYS values. So that's what I'm going to do. So let's start. So first boundary condition that I'm going to apply is one end is fixed and other end is free. So as usual, go to start menu, and under the ANSYS 19, if you can find mechanical APDL, click on that and you'll find this screen here, right? Now click on preferences, click on structural, okay, then go for preprocessor, click on element type, add edit or delete, add, and you're going to add the element as beam 2 node 188, and click on OK, and let me close this. Next, you're going to add the material properties, material models, structural, linear, elastic, and isotropic, and you're going to give the input values 2E5 and 0.3, right? So these are the 2 values, and click on OK, and I'll close this. Next, go for sections, B, common section, and my breadth value here, it is rectangular cross section I have here, as you can see in the problem, right? And of breadth 300 mm and height 500 mm. Whereas unlike in cantilever or simply supported problem where you will shift this H and B, you will interchange this H and B while giving as input in ANSYS. Here you need not do any kind of things. You can directly input B as 300 and H as 500 mm. So I'm going to keep the unit system as mm and the force as Newton. So 300 and 500, and click on OK. Next, go for modeling, create key points. I'm going to create 2 points, which is 1 at 0, 0, 0, and the point number 2, which is at a height of 10 meters, which is 10,000 mm. So that I'll give it in y-axis. Right. Okay. So I have 2 key points. I have to join them with lines, and I'll click on straight lines. I'll click on these 2 points and OK. So the modeling stage is completed. So that's all. Then I have to mesh the problem, meshing, size control, manual size, lines, all lines. So let the number of element divisions, let me take it to be say 100, and click on OK, and let me mesh my problem, mesh and lines, and if you click on this line and if you click on OK, and the meshing is done. So it has been converted to elements. So meshing stage has been done. So then I have to apply the loading condition. So my boundary conditions here are one end is fixed and the other end I have a load of 1 Newton. This is a dummy load which I will apply in order to calculate my critical load, right, or my buckling load, right? Okay. So loads, define loads, apply structural, and displacement. I'm going to apply this key point here. So on key points, click on this key point and click on OK. I'm going to fix here, so which means all degree of freedom is arrested, all the 3 translation and rotation is arrested, and click on OK. Then you are going to apply a dummy load of 1 Newton minus 1 Newton in this key point here. So force of moment on key point, click on this key point, OK, and if you have in the y direction, you are going to apply a value of minus 1 Newton in the downwards direction, right? So this is just a dummy load, right? Okay. Once this is completed, get to the solution, right? So here what you have to do is get to analysis type, click on new analysis and check whether it is in static, right? Click on whether check it and click on OK. Now click this unabridged menu. If you click on this unabridged menu, you can find some more options getting in this analysis type. If it is abridged menu, you'll have only 3 options here. Whereas once you click on this unabridged menu, you'll have some more options occurring here. Under this option, you'll find an option called as analysis options. Click on that. As you come down low, as you scroll this down lower, you can find here an option called as include pre-stress effects, right? So this will be by default, it will be no. Once you click this, it will become yes. You have to click this option of pre-stress here, yes. I have to on this and click on OK. So this is very much important to do in buckling. So once this is completed, click on solve current LS and OK. So and you'll find solution is done. So usually when the solution is done, when we solve this problem and when you find a dialog box like this, you'll close this and you'll directly get to the post processor to see the results. But here in our case, our solution has not yet been done. We have not yet solved our problem for buckling. We have only solved our problem for static analysis. So don't directly go to see the results. Instead, click on this finish. So once you click on this finish, again go to solution, analysis type, again new analysis. You're going to change the static analysis to Eigen buckling. So the buckling what you're going to solve here is Eigen buckling. There are basically two types of buckling what we can do in ANSYS. So one is called as eigenvalue buckling, another one is called as non-linear buckling. Eigenvalue buckling is nothing but a simple ideal buckling analysis that will perform. So I have some paragraph here which you can read later on so that you can get a hold of what it is. And non-linear buckling, when you have excessive displacement, you can go for this non-linear buckling. So in my case, I'll simply solve an Eigen buckling because non-linear buckling is pretty much out of the scope of this video tutorial. I will solve my problem using Eigen buckling. So hence select Eigen buckling and click on OK. So you can find analysis option again. Click on this analysis options. Here you can find the mode extraction method to be block Lancros, and in the number of modes to extract, click on 1 and click on OK. So pretty much don't bother about what is this block Lancros and what is this one. So don't worry about this. This little bit higher understanding level is required in order to see what it is. So as far as now, just follow the procedure and number of modes to extract, click on OK. And once this is done, go for solution, solve, current LS, and again click on OK. Again you can find solution is done. Once you find the solution is done, don't think that again the problem is completed. No, it is not completed yet. So again close this, right? So again you are going to go for one more time. You are going for analysis type, click on new analysis. Again we'll check whether the option is Eigen buckling and click on OK. So there's a warning. Don't worry about this warning. Just close this warning. Again come to solution. Again click on this expansion pause and it will be off. In the expansion pause, it will be default off. Click it to on and click on OK. So once this is done, here under the load step options, click on that and expansion pause, single expand modes. Here the number of modes to expand, give it as 1 because the number of modes to extract were earlier given as 1. Hence the number of modes to expand is given as 1 again here. So click on OK. Again solve the problem. So solve current LS. Okay. So in the entire problem, we have solved the problem 3 times. We have clicked this solve current LS 3 times. Only after doing this, only after completing this, now we can see the results. Now go to general post processor. So plot results and deform shape, deform plus undeform, and if you click on OK, and I'll just zoom out. So we can't find any significant changes. That is because the buckling has happened the other way. So I'll just rotate the view, right? I hope we can't just clearly see here, right? So anyway, so actually, once you click on this deform shape, click deform plus undeform, and if you click on OK, so the buckling has actually happened. And the critical load of buckling is nothing but this fact. So you can find this factor value FACT, which is 0.555 into e power 7. So this is nothing but our critical load value, and DMX is the displacement value. You can find the displacement is very much small. That's why you can't find any change in this shape. So I'll go for this nodal solution and device solution displacement and click on OK. So you can find e power minus 6, which is very much smaller deflection. So don't worry about this. This is not important. What we need here is the critical load of buckling. So which is 0.55 e power 7. It is in the terms of newtons, right? You can also see this value here. List results. Click on the detailed summary and you can find this value, which is 0.555487 e power 7. Which will be approximately 5.548 meganewton. So this is our ANSYS value. ANSYS critical or buckling load value, which is 5.548 e power 6 or meganewton. So 5.548 meganewton. And let me compare it with the theoretical answer here. So the problem that we have solved is one end is fixed and the other end is free, and the answer is 5.552 meganewton. Theoretical answer is 5.552, whereas the ANSYS value is 5.548, which is a very closer match with the theoretical answer. And one thing you have to be very much clear is that while substituting here, you will substitute the Young's modulus to be which is 200 gigapascal, so which is 2 into 10 to the power 5 Newton per mm square. Length is 10 meters, so we'll substitute it as 10,000. While substituting this I, moment of inertia, there are two moment of inertia. So one about IZZ, other about IYY. The value that you have to substitute here is the least of these two value. IYY or IZZ, the least of these two values should be substituted here in order to get the critical load, because buckling occurs in the direction which has the least moment of inertia. Hence, while substituting this side, you have to substitute the least moment of inertia, and you'll get this value. So that value matches with the answer. So this is the first boundary condition that we have applied here, which is one end is fixed and the other end is free. Next we will move on to the next category of boundary condition. So which is, so one end is fixed and other end is hinged. So here one end is fixed and other end is free. The next category is one end is fixed and other end is hinged. So this is the second category of problem that we are going to solve. So hinged means it is nothing but that so all the translation have been arrested, and the rotation of x, rotation of y is arrested, whereas the rotation of z is free, which is nothing but a simply supported condition. So other end is hinged means it is a simply supported condition. In simply supported, we will arrest the three translation and two rotation. We will leave one rotation as free, which is the z direction of rotation is to be free in this case. So that's the same way that we are going to do here. So in order to solve this, I am not going to redo the entire problem again. So I'll use the help of session editor. So because the adding the element and material properties, section properties, and modeling the problem, and pretty much up to meshing, everything remains the same. So I'm not going to redo all those things again. So from boundary condition, I'll delete everything what I have done so far, and I'll do it again. So from up to meshing, what I have done earlier is similar to here, because only the boundary condition is going to change. Everything other pretty much remains the same. So using the help of session editor, this is up to the stage where the meshing is getting completed. So now I'll continue the boundary conditions. So loads and apply structural displacement. So here we are going to apply one end is fixed and other end is hinged. So on key points, so I'm going to fix this end, which is all degree of freedom. I'm going to arrest the all degree of freedom. I'll click on I'll fix this key point, and this key point I have to hinge. So I'm going to provide a hinged support here. Usually for a hinge, we'll arrest the three translation u of x, y, z, and the rotation of x and y should be arrested. The rotation of z should be free. This is a usual hinged. But here there's a slight modification. What you have to do is that you should also leave this u of y direction to be free. U of y is this direction, because as the buckling occurs, the height of this column reduces by a small amount. So you should give the allowance for this column to move in y direction by a small amount. Only then the buckling will happen. Even though this is a hinged support, you have to leave this u of y also free. So u of x and u of z you are going to arrest, and in rotation you are going to arrest rotation of x and rotation of y. So and you are going to leave the rotation of z and u of y free in this part. Okay. So this is one change from the simply supported hinged support what we have seen earlier. So keep this in mind and click on OK. Now I'm going to apply the force on key points and click on this key point, and I'm going to apply the dummy load of f of y direction, which is -1 value, which is already been here, and I'll click on OK. So a load is being applied. Now I'll go to solve. So solution, analysis type, new analysis, check whether it is static. OK. Click on this unabridged menu. Now go for analysis option, and if you come below, you can find the include pre-stress effects. Click on this yes. OK. And everything other things what you have done earlier, that is similar. You are not going to do anything here. So I'm going to solve solution current LS and OK. Solution is done. Once this is completed, I'm going to click on finish. Next, I'm going to come again to solution, analysis type, new analysis, get to eigenvalue buckling, click on OK, and again analysis options, click on this number of modes to extract as 1, and OK. I am going to solve the problem again. So this is the second time I'm solving. click on OK and close. Next, I'm going to go for analysis type, new analysis, and eigenvalue buckling. Check whether it is eigenvalue. Okay. Next, I'll close this. Go to expansion pass. Click on this expansion pass as on. Okay. Load step options. Expansion pass, single expand modes. The number of modes to expand is 1, and I'll click on OK. Again, solve. So this is the third time I'm solving. So in a buckling analysis problem, you have to solve the problem, solve current errors. You have to click this 3 times. So once the third time is completed, the problem is completed. Now I'll go to general post processor, and so in general post processor, click on the plot results, nodal solution, click on OK. So save this result. Actually, so I have to save this result, and this is the value that we are interested. We are not interested to see this deformation. We are interested to see about this FACT factor value, which is 0.452 e power 8. Which is nothing but 45.2 megapascals, right? So you can also see this in list results detailed summary. So you can also save this screenshot. So you can, here it is 0.45211 e power 8, and which is 45.211 megapascal. Whereas my theoretical answer, what we got here is, so this is a problem of one end is fixed and other end is hinged, and my answer is 44.4132, and my ANSYS value is 45.211. So 44.41 and 45.21, it is a closer match. So the second is also over. So first one is one end is fixed and other end is free. So this one that we have completed. Okay. And the second one end is fixed and other end is hinged. So this one also we have completed now. So 2 more boundary conditions to go, right? So once this is done, next again, I don't need to redo the problem once again. So I'll use the help of session editor. So still meshing, everything remains the same. So after meshing, I'll delete all the things. So where is the meshing? Okay, here it is. So L mesh. So after this, I will delete everything. Still meshing, you have all the same one. Okay, and click on right. Okay. Now the third boundary condition which I'm going to use is both ends are fixed. So this is the third boundary condition that I'm going to apply. So again, go to preprocessor. Till meshing I have completed. So I'll go for apply structural displacement on key points. I'll click this key point. Okay. And so as it is fixed, I'm going to give the all degree of freedom to be 0. So all DOF and displacement value is 0, and I'll click on OK. Next, again, both the ends are fixed in this case. So I'm going to click on displacement on key points, and the top key point, I'll click on OK. So here, even though it is fixed, you should not give the all DOF as 0. So all DOF pretty much means U of x, U of y, U of z, rotation of x, rotation of y, rotation of z. So all these are 0. So instead of selecting all these 6, I will select all DOF. So that is the meaning of fixed boundary condition. Even though both ends are fixed, in the topmost region, as I already told you, in order for the buckling to occur, this key point should move a little bit. It should have the freedom to move a little bit in y direction alone. Hence, even though it is a fixed or hinged, you should give the allowance for the key point to move, or else the problem will not solve. So hence, you have to leave this u of y. Even though it is a fixed boundary condition, you should leave this u of y alone to be free, and all the other degree of freedom should be fixed. And I'll click on OK. So keep this in mind while solving this problem. And again, click on pause on key points, and I'll click on this key point. I'll click on OK, and in f of y direction, I'll apply a dummy load of -1 Newton. I'll go for solution, analysis type, new analysis. So it is in static. I'll click on this unabridged menu, go for analysis option, and once you come here, you can click this include pre-stress effects to on, yes, and OK. Now I'll solve the problem. Solve current errors and OK. So once this solution, so this is the first time I'm solving the problem. So once this is completed, go for finish. Next, again come to solution, analysis type, new analysis, Eigen buckling, and click on OK. Now analysis options, number of modes to extract, I'll give it as 1. I'll click on OK. Now I'll again solve the problem. Solution, solve current errors, and OK. So this is the second time I'm solving the problem, and again go to analysis type, new analysis, check whether it is an Eigen buckling. It will be by default, it will be an Eigen buckling. So click on this expansion pass, and expansion pass to be on. Okay, then load step option. expansion pass, single expand and expand modes, number of modes to expand to be 1, and I'll click on OK. Once this is completed, I have to solve the problem again. So solution solve current LS. Okay, so this is the third time I'm solving the problem. Once this is completed, the problem is solved. Now go to general post processor. So now go to general post processor, click on plot results, control plot nodal solution, displacement vector, and OK. So save this result, and but what we are interested is this value, which is 0.881 e power 8, which is 88.1 meganewton. So to see this value more clearly, come to list results and detailed summary, and here you can find. So the exact answer is 0.88074 e power 8, which is 88.074 meganewton. So this is our ANSYS value. 88.074 meganewton is our ANSYS critical buckling load or a crippling load. So in theoretical, let's see the theoretical answer, and here it is. For both the ends fixed, so I have my theoretical answer to be 88.8264, and the ANSYS value is 88.074, which is a closer match. So 88.8264 is a closer match with 88.074. So the third boundary condition have been completed. So this is my third boundary condition, and finally I have the last boundary condition, which is both the ends are hinged. So for the last boundary condition, so again I'll use the help of session editor. So till meshing I'll keep, and the rest I'll delete and I'll redo again. So till meshing, so this is the area where meshing is completed. So till meshing I'll keep, and the rest I will delete it, and I will solve once again, and I'll click on OK. So meshing, till meshing is completed. So the last boundary condition that we are going to see is, so the last boundary condition is both the ends are hinged. So right, so we'll solve this. Now I'll go for so once the meshing is completed, so I'll go for loads, apply structural displacement, and I'll click on key points. As it is a hinged support, so in this hinged support I'm going to click on OK, and here you can find hinged means all the displacement are 0 and the rotation about x and y are 0. The rotation of z should be free, right? So this is a hinged support, so I'll click on OK, which is nothing but a simply supported condition, right? Again, as both the ends are hinged, I'll go for displacement on key points. I'll click on this and click on OK. Here, as I already told you, this key point should have the allowance to move in y direction a little bit. Only then buckling will occur. So hence, even though it is a hinged support, I should leave this u of y to be free. So I am going to fix u of x, u of z, and rotation of x and y to be 0, and I'm leaving this rotation of z as free because it is a hinged support, and I'm leaving this u of y at this location to be free because this key point should move in a little bit in y direction. So only then the buckling will be occur, right? So I'll click on OK. So once the boundary conditions are applied, I'm going to apply the force on key points. So I'm going to apply the dummy load of -1 Newton in y direction. So in f of y, I'm going to apply a value of -1 and click on OK. So now I'm going to solve the problem. Solution, analysis type, new analysis. So it is in static. OK. In unabridged menu, you have to go for analysis option, and once you come down here, you can find the include pre-stressed effects, yes, and click on OK. Now solve the problem. So solve current LS and OK. So this is the first time I'm solving the problem. Close. OK, and again finish. Now go come for solution, analysis type, new analysis, click on Eigen buckling and click on OK. Now the analysis option should be the number of modes to extract is 1, and click on OK. Now solve the problem again. So this is the second time I'm solving the problem. OK, and close, and again analysis type, new analysis, and check whether it is Eigen buckling. OK, and go for expansion pass to be yes. OK, next load step option, expand modes, the number of modes to expand should be 1, and click on OK, and finally solve it again. So solution solved. So this is the third time I'm solving. So once the third time solution is completed, solution is done, I can see the results directly. So go to general post processor. So go to general post processor, under plot results, deform contour plot nodal solution, displacement vector sum, click on OK. So this is the plot where I am interested to see this factor, which is 0.22222 e power 8, which is 22.2 meganewton. So in order to see a clear value, go for list results, detailed summary. Here it is. So 0.22159 e power 8, which is 22.159 meganewton. So that's the crippling load, and which I can find it here. Yeah, here I have 22.2066 meganewton. Here I have 22.159. So which is a very much closer value with the theoretical. So I have also completed the last boundary condition. So that's all. This is how you solve a buckling problem this is how you determine the buckling or crippling load for a long slender column. So once again, thank you. So this is the end of this video tutorial. So until again in another video tutorial, I'll see you once more, right? So thank you. Signing off is Shankar. See you. Bye.